Welcome to the Saving Stormwater podcast. Part of the reason I'm able to do this podcast is because of ComplianceGO. If you haven't heard of it before, ComplianceGO is situated to handle the inspections, communication, and task management behind all the major stormwater processes in every industry. Make sure to check them out in the podcast description. For today's Stormwater podcast, I'm pleased to be joined by Sean Ahearn. Did I say that right? I don't think I ever actually asked you how to pronounce your last name there, Sean.
Ahearn, it's all fine as long as you don't call me late for dinner.
Yeah, well, we're kind of in different states, so that might not work out very well. Would you mind describing a little bit about who you are, what you do? You're a project manager at Beta Analytic. Tell us a little bit about yourself.
Yeah, I am a project manager at Beta Analytic. I am a geochemist, and what we do at Beta and what I do for Beta is I use isotopic data as evidence to fingerprint and track not only water sources, but also the contaminants found within those water sources.
Great. Okay, so a little bit of context there. Today's Stormwater podcast theme is about being stormwater detectives. So, stormwater private investigators, we're going to be kind of focused on solving stormwater mysteries. And if you're like me, when you heard about the concept of using isotopic fingerprinting to solve stormwater mysteries, it all kind of seemed like voodoo. And we're going to talk a little bit about that. Sean's going to, we're going to talk a little bit about some of those aspects. But first, I wanted to get kind of deep into it. What is particle fingerprinting and how could it be used in stormwater management mysteries?
All right. Well, isotopic fingerprinting, it's a term that's used to describe that isotopic values are characteristic of an element's origin. And that can either be in time or in space, depending on what isotope you're measuring. An isotopic value, generally speaking, it's a mass ratio of elements like oxygen, hydrogen, nitrogen, all these things that are all around us all the time. And these values are compared to sets of national and international standards. So we're able to look at this not only nationally, but internationally when we're comparing these data sets, which makes it very useful in trying to solve these kinds of mysteries. The value expresses the difference in mass ratios. In stormwater management, we can use these isotopic values to track water volumes and contaminants into and out of the watersheds and into water management systems. So since local stormwater differs isotopically so differently than groundwater sources or marine sources, or even municipal water sources, depending on how the water is treated, we can use these isotopic values to differentiate between the sources into and out of systems.
All right. Yeah, absolutely. So when you first approach cities or regulating authorities or anybody that could use isotopic fingerprinting, what are some of the first steps that you get into with some of these I kind of analyzing data values, I guess?
Well, I think the first thing that people happens to people when they hear about isotopes is that they think it's like you said, like voodoo, like some kind of magic, or that it would be impossible to be able to source a water using a value like this. So really, the first step is education. A brief background on the concept, the fact that this sort of technique is not brand new. I would say that the technology that we use today to measure isotopes is cutting edge. But originally in the early 60s, this is a technology that's been refined over a good amount of time. I've been fortunate to have met a lot of people who use isotopes in their research. So I'm able to sort of pull from the lab how people can use it in their everyday steps. And then, once people sort of understand that, okay, this is actually a pretty well used technique, it's a solid chemical analysis that's not necessarily something that Beta Analytic made up or that I'm pitching to them as something that is brand new. It's to dive into what their issues are. Are they dealing with inflow and infiltration issues? We can use isotopes to determine the volume of their stormwater infiltration to their systems. That can save them a lot of money and time understanding what's actually happening. By measuring the water or the dissolved constituent in water, like nitrate, we can produce models that suggest the amount of contaminant that can be coming into and out of a target area. Um, and right now, currently, when you're doing these tests, if you're trying to figure out where your problems are, they're fairly laborious. You have to use cameras, smoke tests. It takes a long time. People have to, maybe install monitors and stuff like that, and it takes a lot of time and energy to do. Whereas with testing water samples in areas that are already present, storm sewers that are already present, taking some, water samples, rain samples, we can begin to plug these values into models and help create maps so you can try to actually figure out where your high risk areas are.
Okay, yeah, that's really I'm taking a second to kind of wrap my head around that. So, what are some of those kind of everyday steps that I guess people are doing already that can involve isotopic fingerprinting?
Well, everyday steps, right now, when you have an area that's constantly infiltrated with storms, you're counting on your stormwater sewer to collect all that water. And we know that in a lot of cases there's overflow, which is a designed feature of it, but then there's also your infiltration. So right now you have your municipal sewers pumping a lot of water that may not need to be treated in the same way. And every day pumping rates are variable in areas that have constant inundations of stormwater. So this, it kind of goes back to the SSI thing or ISS, or I forget how it is, infiltration stormwater. That those things can really be useful for that.
So, in the October podcast, for example, we talked with Susie Housley from Storm Sensor about the benefit of data in water management. With our conversation that we had earlier, you discussed solving otherwise unmeasurable data issues. What are some of those issues that can be solved through isotopic data or other information to help address water quality issues?
Well, like I'm sure Susie mentioned, data is your friend, and you can never have too many friends. So when we talk about using isotopes to measure water volumes, we're talking about taking advantage of really basic scientific principles, um, mostly the conservation of mass. Unless you can, up till this point, you cannot, spontaneously create or destroy atoms. They're just moved around in different phases. And that being said, traditionally, when we're performing a mass balance, we want to use something that's dissolved in water, like salt. And marine water is very salty, brackish water is less salty, fresh water is not salty at all. So if we have three different water sources and I start mixing them to a jug, right, what I could do is I could measure the amount of salt in an unknown sample and suggest the amount of each type of water I would need to get to that salinity at any given volume, right? That's a very common way to use this kind of data to solve these unknowns, right? Now, what's really interesting about water is that it undergoes phase changes, the water cycle, evaporation, condensation, ice. And what'll happen is it'll pick up and drop some of these ions, right? Like salinity, like salt, right? So this makes traditional mass balance equations lacking some critical fluxes. So, for example, evaporation, which we know is a huge outlet for water, especially on street surfaces and in agricultural areas. When you have a salinity model or a mass balance model using salinity, you actually lose that flux. So it has to be estimated. Now, what's interesting about using isotopes is that we can actually measure the water vapor in an area and suggest the mass of the water that's leaving, meaning that we can actually plug this value into our water budget mass balance that we're making, and we can go ahead and actually begin to understand all of the fluxes in our system, and that can help us measure things that we can't really measure. Like, for example, groundwater infiltration in an isolated lake is very difficult to measure. You have to install piezometers, wait a lot of time, get a bunch of data back, and then start your model. What you could do in a different way is use isotopic modeling and suggest, well, you need this amount of water at this value to get to this mass. And you can begin to start answering these questions a lot faster and with a lot less effort. Where I live in Florida, we have a lot of water and it's not all connected to rivers or streams. A lot of these things have to be measured in different ways to be able to get to the answers that we're looking for.
Okay, yeah, so I can see that having a couple of different impacts, specifically with municipalities. They do a lot of the stormwater sampling and just water sampling in general, and I can see that having a big benefit in terms of point source versus non-point source pollution. Um, I Are you familiar with those terms?
Yeah, definitely.
Yeah. Okay.
And actually, when you bring that up, it makes me think, When we use isotopes in mass balance models, we're dealing with quantity issues. When we use an isotope like a nitrate isotope, where we're measuring the nitrogen and the oxygen isotopes, we can actually address water quality issues. And with that kind of technique, we can begin to determine whether or not we have a point source or a non-point source infiltration happening. And what we can do is create isobar maps and either bring us back to that point source, or at the very least be able to define an area that is our non-source point and begin to understand and model its impact on the environment.
Awesome. Yeah, I think that'd be especially valuable for, municipalities that might not necessarily live um, right next to lakes or rivers or streams or anything like that, but do know that they have areas where they're getting stormwater pollution when it rains for whatever reason, and they don't exactly know where it's going or where it's coming from. I can see that as being very valuable.
Yeah, that's exactly what it is that we're trying to help people do, is instead of having to focus on these models that are, in some cases lacking some critical fluxes, we try to close these gaps and help people come up with the best model so they can, prepare their city or their county or their state for, for the inevitability of big storms and a changing climate.
Hmm. Hmm. Um, so one thing I did want to bring up with you today, I was reading. I do a little bit of research every morning, just in terms of what's happening around the United States and around the world, in terms of stormwater pollution and runoff. Today I was reading an article about um, LA water pollution and identifying it to stormwater, and we were talking about this a little bit before the podcast. And the article is great, and it talks a lot about kind of the fiscal responsibilities and some of the municipal responsibilities and what it means in the short term. But some things that kind of didn't get addressed that we try and talk about a lot in the stormwater, I guess, industry, or the kind of the stormwater sector, is algal blooms. And there's a lot of mystery behind that. And, in our conversation before the podcast, you mentioned that there's even some debate. Do you think you'd be able to address some of the mystery behind algal blooms?
Definitely. One of the biggest debates behind algal blooms forming right now is what the actual trigger is. And what scientists debate is whether or not it's just a total nutrient load thing and sunlight load, or if there are other mechanisms like maybe trace metals that actually activate the bloom. Furthermore, in an area that is prone to blooms, you might actually have different species bloom in the same area in different years, meaning that we can't actually predict what type of microbe is going to bloom. So these are all kinds of different problems that we're trying to address. When it comes to how isotopes can relate to illuminating these kinds of issues, is what we talk about when we talk about monitoring. If we're regularly measuring an isotopic value and a bloom occurs, what we can do is we can use isotopic data to begin to understand the role that the nutrient played in that bloom. Was the nitrate actively uptaken? Was it not? Was this a bloom that actually was only phosphorus limiting, or was it a bloom that in fact bloomed solely because there was excess nitrogen present? And when we start identifying what the drivers are, we can begin to actually use remediation plans that are going to be effective. Right now in some areas, I know in Pinellas County, they had great success with their fertilizer ordinance because they were able to actually determine that they did have excess fertilizer going into their waterways. Whereas in other cases, like Lake Okeechobee, for example, there's actually a lot of interesting data out of Mote Marine Laboratory that suggests that just because it was a large amount of discharge into the Gulf of Mexico from Lake Okeechobee does not necessarily mean that there will be an algal bloom. There have been seasons where there is little or no discharge, and we have blooms all the same. Now, when we talked about that California article, what I thought was really interesting was that they identified, whether they know it or not, both of the issues related to stormwater quality, and that is the short-term health effects, meaning, it's poor water quality can get you sick. It could be full of a bunch of bugs that have, run off from either septic systems, sewers, or even just, regular urban debris that gets washed out. But then that long term, the fact that those nutrients sometimes actually end up hanging out in the soils for a long time, and they're just kind of there waiting for the next opportunity to be utilized. So what we like to do and talk to people about and how we help them address the mystery is by actually defining the role of the nutrient and where is the nutrient and using that fingerprint to suggest that it is the source you think it is. And when you finally take steps to remediate, we can continue to monitor that nutrient and ensure that your goal of removing that particular source is effective. And in doing so, you're able to really understand whether or not the amount of, like you talked about monetary and time and effort, whether or not it's really making an impact on your remediation effort. So I think, maybe the key word there with the mystery behind algal blooms would be, with isotopic data, you can begin to understand the impact that the stormwater runoff is having on water quality and whether or not it is linked to something like algal blooms.
Okay, yeah. So you mentioned areas prone to algal blooms. Is there a specific type of area that's more prone to blooms? Is there, if you're not prone to blooms, is it still something that you need to keep aware of? Just I kind of wanted to get your thoughts on that. You mentioned it earlier.
Yeah, well, so when you talk about where you are and where you are not prone to blooms, you need to break it down to the types of algal blooms that there are. So you have red algae, green blue algae, and brown algae. Right, your brown algae is that big marine stuff, your sargassum, those things that float in rafts out in the ocean. That's one kind of algal bloom. You have your red tide algal bloom that is also a marine type of algae, but those, since they're found predominantly in the Gulf of Mexico in the Florida Southwest area, but those they can actually with currents and winds move all around, and those are the scary ones because they cause fish die-offs and they're very dangerous if they're consumed. And then your blue-green algae are more prone or found in your, canal areas, back reef lagoon areas. So when it really breaks down, any sort of environment can be prone to an algal bloom. It just the species might be a little different, or the color might be a little different. But all areas, if there's water present and if light can penetrate through it, you're basically just have to perturb the environment in any particular way to get that bloom to come out. And that's what people are working on now. That's what they're trying to figure out is what is that trigger in water quality
Mm.
that actually causes these things to arise. And why is it that, in 2012 it was one species and in 2013 it was another. And these are things that people are working on now. And once we are able to start answering these questions, which there's a lot of great research that's going on now, we'll be able to start to integrate those solutions into stormwater management, right? So that way we can begin to ensure that our internal mechanisms to move and clean and ensure that this water is going to where it needs to go, we can also make sure that we're preventing things like algal blooms.
That's great. Um, yeah, I'm really glad you cleared that up for me. I'm not sure. Maybe some of our listeners are a little bit more knowledgeable than I am.
Well, yeah, well, blooms are really interesting. There's so much research happening, and I think that this is the kind of scenario where the more research is done, the more questions are asked and maybe not answered. So it's really interesting. It's an interesting time to be an algae, to be a microbe.
Right,
Yeah.
right. So another conversation we had before the podcast, this was a little while ago, not right before the podcast, but we talked a little bit about radiocarbon and the potential for solving stormwater mysteries there. Um, could you give me just kind of a glimpse into how that works?
Yeah, sure. Well, when we first started talking about isotopes and how they can be used to solve water mysteries, we started talking about stable isotopes, and those are the ones that are conserved, but phase changes just move the masses around, right? And because something like evaporation and precipitation affect those masses, we can use them to track where things are going and where they came from. Radiocarbon is unique in that it's more time related. And with radiocarbon, in the upper atmosphere, nitrogen molecules are bombarded by cosmic rays and radiocarbon is formed. So everything now that is living, eating, breathing, drinking, we all have a modern carbon signature, right? And once we cease to exist, we cease to be intaking all this carbon, that's when the clock starts. That's when now radio decay begins to start, right? Now, the way that we can use this in water sources is when we are investigating something like a water well, we can use the apparent age, and that is the age of the carbon found in that water, to suggest about how long this water has been on the surface of the planet, furthermore, underground in an aquifer, and we can begin to address whether or not this water source is consistently coming from the same place, right? So if we're in Minnesota, we're getting glacial melt from Canada and it's coming down, we can consistently see that this water took maybe 1,000 years to get there, right? Or I think there are also good examples in Kentucky where there's a lot of groundwater infiltration that takes a very long time before it finally arises there. That's why they make such great bourbon. Um, right? But now let's say we're monitoring this well, and then all of a sudden, 1,000-year-old water that we measure maybe once a year, all of a sudden is 200 years old, right? Now that is bizarre. And what that could suggest is maybe we're over exploiting this well and we've actually had stormwater infiltration come and we're over exploiting it. So we're pulling in more water than the recharge rate is. So we're pulling in water that has not had time to be chemically and physically filtered by these aquifers. And that water could be potentially non-potable. And we would have to do a lot more work to get that water to a level where it could be used for consumption or even agriculture. So it's just another way of tagging the water. So in one case, we're using the water itself. In another case, we're using a contaminant like nitrate. And in other cases, we can use the carbon present in natural waters to understand where they're coming from and where they're going and help us identify whether or not we've overexploited a well or if some kind of contaminant has entered a drinking water well, through a massive storm event or maybe even a mass wasting, like when you suddenly lose a lot of ground cover, like in a landslide, right? That
Mhm.
suddenly changes the pressure on your aquifer, and that suddenly, that storm may have had a much larger impact on the groundwater than was previously thought. And the radiocarbon age would suddenly shift, and it would be an indicator that, hey, something changed.
Okay, yeah, that makes sense. So that kind of leads me into a different. I read an article recently, and quick shout out to Luke Owen on LinkedIn. He's the one that shared this article, which helped me find it. But it talked about poking and prodding in terms of stormwater management and identifying. Um, would you say that stormwater or fingerprinting could be used to assist in supporting the need for change in kind of the status quo in terms of needing to poke and prod?
Yeah, I think that the isotope measurement and water quality has definitely not been as pervasive as it could be. And I think that it can definitely lead to a new understanding of particular environmental services that we think are actually happening. The first thing that I think of is biofilters and biofiltration. So there's this idea, this concept, and it's the University of Vermont has a really interesting study that came out recently, and a couple more um, that discuss this idea that biofiltration has the use of biofilters has outpaced our knowledge of biofiltration. And what this researcher Stephanie Hurley discovered was that in some cases the biofilter was actually leaching the contaminant as opposed to absorbing the contaminant. Right. And that's really scary when you think that, everyone is leaning towards green infrastructure as opposed to gray infrastructure as a solution. And some of these biofilter designs are either outdated or just not well understood. And we're putting them everywhere. And in some cases, they're actually the source of our contamination as opposed to the solution. And we've actually worked on some biofilter case studies where we found the isotopes to really illuminate what's going on inside of the biofilter. So as opposed to it being this, I'll call it a green box, where storm water comes in and then clean water comes out, we can actually take that box apart, look at it up and down and left and right, squeeze the water out and measure it for its isotopes and look at what kind of reactions have been imposed on those isotopes. And then we can begin to actually understand what was going on in this biofilter. Did most of the reaction happen at the top? Did it mostly happen at the bottom? Do we see any difference in trending? Is it maybe that a biofilter is much too large or much too small? We know that all biofilters are not the same. We know that what works in Nevada is not going to work in Miami, and that's just because the plant biota is so different, meaning that they all need to be constructed differently. So I do think that we can definitely shake things up and change the status quo by just simply poking and prodding and trying to understand a little more and maybe say, hey, like let's just measure these isotopes and prove to me that there's the change that you expect there to be. And an isotope is a great tool to be able to do something like that.
That's phenomenal. That's awesome. So we are getting kind of close to our time frame that we have with this podcast episode. Um, So I kind of want to give you the last final say here. What's one thing that you would impart on our listeners today?
Ooh, okay. Well, there's an urgency now more than ever to understand our water quality issues. And I think that what we're learning more and more is that these temporary patches and coming at problems at their sinks isn't good enough anymore. We need to start understanding problems at their source. And furthermore, we need to make sure that our remediation efforts are actually doing what we think they're doing. And I think that that data-driven solutions are going to be our best tool to protect our most valuable resource, water. And chemical and isotopic data will be and will continue to be key in saving stormwater. Thanks.
Yeah, thank you so much, Sean. I really appreciate having you on. I would love to do it again.
My pleasure.
So just kind of for everybody, we're super glad that you took the time to listen. Make sure to check out Compliance Go. They're part of the reason why I'm able to do this, and they're part of the reason why we get to have these conversations that can really help out the stormwater community. Thanks so much, Sean.
Yeah, and let's not forget Beta Analytic.
Oh yeah, absolutely. Beta Analytic. Quick shout
Yeah.
out there, right?
Beta Lab Services and radiocarbon.com.
All right, there you go. All right, well, thank you so much.